So for problem number 15, we are doing three things. We're finding the intervals on which a function is increasing and decreasing, the local maximum and minimum values using either the first or second derivative test, and why not, we'll use both in each of these cases, and three, the intervals on which the function is concave up or concave down. Fantastic. So I guess I'll break this up into three videos. It probably makes sense, because each of these is a fair amount of work. So first we're going to look at 15a, which is x squared e to the x. F of x equal to x squared e to the x. So first, to find where it is increasing or decreasing, we take the derivative and we apply the product rule here. 2x e to the x plus x squared e to the x. The derivative of x squared is 2x times e to the x plus x squared times the derivative of e to the x, which is e to the x. And really we should be concerned with what the domain of the original function is, but it's all real numbers. And now we say, where does the first derivative not exist, or where is it equal to 0? This always exists, so we just have to set it equal to 0. I can factor out e to the x, and I'm left with 2x plus x squared. In fact, why don't I also factor out an x? So I'll factor out an x, and I'm left with 2 plus x equal to 0. Now, when is this ever equal to 0? Well, e to the x is never equal to 0. Either x is equal to 0, or 2 plus x is equal to 0, which says that x is equal to -2. So what this does for us is it breaks the real number line up into three intervals, from -infinity to -2, from -2 to 0, and from 0 to infinity. So first, to figure out where it's increasing and decreasing, I will choose a test point from each of these intervals, say -3, -1, and 1, and I'll plug it into each of the factors of the derivative, and then I'll figure out whether each of these things is positive or negative, and then finally that will tell me whether the derivative itself is positive or negative. So I've got a table. Let's see, my factors of the derivative are e to the x, x, and 2 plus x, and I'll write a final row down here for the derivative. -3, when I plug it into the e to the x, is positive. -1, same thing. 1, same thing. E to the x is always positive. -3 is negative when I plug into x, so is -1, and 1 is positive when I plug it in there. -3 plus 2 is -1, that's negative. -1 plus 2 is 1, that's positive. 1 plus 2 is 3, that's positive. Great. Positive times negative is positive. Positive times positive is negative. Positive all the way is positive. So that means that the function is increasing on this first and third interval, so the interval from -infinity to -2, and from 0 to infinity, and is decreasing on the other interval from -2 to 0. Great, fantastic. Okay, so this actually also tells us by the first derivative test what is happening at -2 and 0. The first derivative test says wherever the derivative changes sign, we have maximums or minimums, local maximums or local minimums. At -2, the derivative changes from positive to negative, so we have a local max, and from at 0 changes from negative to positive, so we have a local minimum. Let me write that down. So at x equal to 2, -2, let me just rewrite that, -2, f prime of x, it goes from positive to negative, which means that we have a local maximum, and at x equal to 0, the derivative goes from negative to positive, so that means that we have a local minimum. Great. We could also use the second derivative test. The second derivative test would say, well, first compute the second derivative. Remember, our derivative was 2x e to the x plus x squared e to the x. the derivative of 2x e to the x is 2e to the x plus 2x e to the x. That's from the product rule. The derivative of x squared e to the x is again 2x e to the x plus x squared e to the x. So combining like terms, this is 2 e to the x plus 4x e to the x plus x squared e to the x. So the second derivative test says let's plug in the places where the derivative is equal to 0. F double prime of negative 2 is equal to 2e to the negative 2 minus 8e to the negative 2 plus 4e to the negative 2, which is, when you add it all together, negative 2e to the negative 2. Since e to any power is positive, this is negative. Remember, the second derivative of the test says if the first derivative is 0 and the second derivative is negative, then we have a, well, local maximum, which agrees with what we had before. And if I were to plug in 0, this is really a lot easier to figure out. If I plug in 0 into here, 4 times 0, e to the 0 is 0, 0 squared times e to the 0 is 0, so I just am left with 2 times e to the 0, which is just 2. That's positive. The second derivative test, if you have a positive first derivative, a second derivative, and your first derivative is 0, then you're at a local minimum. Great. We also need to look at the second derivative in terms of figuring out concavity. So again, our second derivative is equal to 2e to the x plus 4x e to the x plus x squared e to the x. And we set this equal to 0, and I can factor out e to the x, and I'm left with 2 plus 4x plus x squared equal to 0. So either e to the x is equal to 0, which again doesn't happen, or this polynomial is equal to 0. X squared plus 4x plus 2 is equal to 0. Now, when is this equal to 0? You could try to factor it, but it's not going to work out. So you're really stuck with using the quadratic formula. The quadratic formula says that x is equal to negative b, which is negative 4, plus or minus the square root of b squared, 4 squared, minus 4 times a times c, which is 4 times 1 times 2, all over 2 times a, which is 2 times 1. So this is negative 4 plus or minus the square root of 16 minus 4, which is 12, over 2. And you can simplify this down to negative 2 plus or minus the square root of 3. So this is where the second derivative is equal to 0. The second derivative is defined everywhere else. So if I make these the endpoints of some intervals for the real number line, this will tell me where I can, the intervals on which the second derivative are always positive or always negative, which will tell me about concavity. So great. So here, I'm just going to erase everything except for these two values. Fantastic. So this tells me that, done. This tells me that I need to look at the intervals from negative infinity to negative 2 minus root 3, and the interval from negative 2 minus root 3 to negative 2 plus root 3, and then the interval from negative 2 plus root 3 to infinity. And from negative infinity to minus 2 minus root 3, why don't I choose the number? Minus root 3 is, it's bigger than negative 2, so why don't I choose negative 4 here? Negative 2 minus 3, what's between negative 2 minus 3 and negative 2 plus 3? The easiest thing for me to figure out is negative 2. I think negative 1 is also in there, but whatever. I'm going to do negative 2 because it's easy enough for me to figure out. It's in there. Negative 2 plus root 3. Root 3 is less than 2, so this is a negative number, so 0 is in here. I plug these into the second derivative. So f double prime of negative 4 is equal to e to the minus 4 times, let's see, 2 plus 4 times negative 4 plus negative 4 squared which is e to the minus 4 times 2 minus 16 plus 16, so that's times 2. That's positive. That means we're concave up on this interval. When I plug in the negative 2 into this, I get e to the minus 2 times 2 plus 4 times negative 2 plus negative 2. Come on. Negative 2 squared. I mean, I already evaluated this when I did the, I guess the second derivative test, but whatever. This is equal to negative 2 e to the negative 2. That's negative. So that means that it's concave down over here. That looks like a z, but that's supposed to be a 2. Okay. And f double prime is 0. Again, I already figured out that that was equal to 2e, or just 2. So that's positive. That means we're concave up over here. Great. Fantastic. That's it.